Friends, now we shall summarize the chapter real numbers of 10th maths. So first, what is real numbers? Real number is nothing but which has both rational numbers and irrational numbers together are called as real numbers. So here we broadly the numbers in the real numbers are classified as rational numbers and irrational numbers. Rational numbers are those which can be expressed in the form p by q where q is not equal to 0. And irrational numbers are those which cannot be expressed in the form p by q where q is not equal to 0. For example, pi, root 10, root 2, root 3, 1.243487. Then these rational numbers also includes natural numbers like 1, 2, 3. Whole numbers where along with natural number 0 is also included in these whole numbers. It also has integers, positive integers and negative integers. So these are all called as, these all set is together is called as rational number. To understand the basic difference between rational number and irrational number, let us take this example. Now here 9.4545 is written here, and here we have another decimal expansion 1.243487. Now you can see, you can observe here what the difference here is. So here you can see it is non-terminating, so we are getting continuously reminder here, but whereas you can see the quotient is repeating in some pattern, with some pattern 4545 like this, it keeps on repeating. So this number, this type of decimal expansions are called as recurring and non-terminating, but whereas here it is non-recurring. So here you don't find there is no fixed pattern here, so it is called as non-recurring, and it is also non-terminating. So such numbers, non-terminating and non-recurring, are called as irrational numbers, but whereas non-terminating and recurring are called as rational number. That is the basic difference you can understand between the rational number and irrational number. So we shall also have a look at definition of rational numbers. Rational number, the numbers which can be expressed in the form of p by q where p and q are integers and q is not equal to 0. Denominator is not equal to 0. Irrational numbers, the numbers which cannot be expressed in the form p by q where p and q are integers and q is not equal to 0. Real numbers are those numbers which has both rational numbers and irrational numbers are said to be real numbers. Then we also need to know what is Euclid's division lemma. Lemma is a statement which is used for proving another statement. So what is this Euclid's division lemma? Given positive integers a and b, there exists unique integers q and r such that a equal to bq plus r, where r is greater than or equal to 0 and less than b. So what it means, what actually it means. Now you know we are familiar with the division in the arithmetic. Suppose if I am dividing some number which is nothing but dividend is divided with divisor, so you know that it is nothing but can be and we get some quotient and a remainder after dividing that. So that is nothing but we can express this as dividend equal to divisor into quotient plus remainder, and this remainder can be 0 or it can be greater than 0 but less than divisor, so which we already know in the division. So the same division is expressed in this algebraic form as a equal to bq plus r, where a is a dividend and b is a divisor, q is quotient and r is a remainder. So using this Euclid's division lemma, we can here an algorithm is developed to find the HCF of two positive integers. So here in this example, c and d are two positive integers where c is greater than d. So how to find the HCF of these two positive integers? So applying Euclid's division lemma, we know that c equal to dq plus r, where r is greater than or equal to 0 and less than d. So that is c is a dividend here, d is a divisor, q is a quotient and r is a remainder. So if suppose r is equal to 0, then d becomes, the divisor is the HCF of c and d. But if it is not, remainder is not equal to 0, then again we have to apply the division lemma to d and r. So d becomes dividend and r becomes divisor. So like this the process continues till we get the remainder 0. Once the remainder becomes 0, the divisor at that stage becomes the required HCF. So this is how we can have we can find the HCF of two positive integers. Then we need to know what is fundamental theorem of arithmetic. So we know that any composite number can be factorized, and it can be the product of the primes. So prime numbers product is unique, and except for the order in which prime factor occurs. So the prime factorization of a natural number is unique except for the order of its factors. What it means, so in general we can say that a composite number x is nothing but equal to product of prime numbers, here p1, p2, p3 up to pn. So these are all the prime numbers, and their product gives me a composite number x. Now so here an example 32760, if it is factorized, and these factors are all prime numbers. So prime number is nothing but which cannot be further factorized. So 2 into 2 will get, so once we factorize this, we get 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. So that means I can express in the form of powers. 2 to power 3 into 3 to power 2 into 5 into 7 into 13 gives me 32760. Here you can observe 2, 3, 5, 7, 13, they are all prime numbers. So their product gives me this composite number. So that's what fundamental theorem of arithmetic says. Then let us know what is HCF. HCF is a product of smallest power of each common prime factor in the numbers. So using fundamental fundamentals of arithmetic of factorization. So here you can see, let us what this means. So suppose if I have to find HCF of 6 and 20, I will factorize in terms of the prime numbers. So here I can get 2 to power 1 into 3 to power 1. Similarly for 20 is nothing but equal to, in terms of prime numbers product, 2 into 2 into 5, that is 2 square into 5. So here HCF will be this small, what are the common here? Common is only 2 to power 1 here, and 2 is common prime number between these two numbers, but here we have to select the lowest power. So here lowest power is 2 to power 1. So 2 to power 1, that is nothing but equal to 2 is the HCF of 6 and 20. So that's what it means, product of the smallest power of each common prime factor in the numbers. Then LCM. What is LCM? LCM is the product of the greatest power of each prime factor involved in the numbers. So I have 6 and 20 already, as per fundamentals of arithmetic, we have written in terms of prime numbers product. So here what it means, you can see we have the factors here, but we have to choose the primes which has highest power. So out of these two, so 2 square is the having greatest power, so that is taken, and other prime product is added here to find the LCM of 6 and 20. So x6 and 20 LCM becomes 2 square into 3 to power 1 into 5 to power 1. So 2 to power 1 is not taken because we have to consider the greatest power. So that's what it means. LCM is a product of the greatest power of each prime factor involved in the numbers. So that's how we will be able to find by applying the fundamentals of arithmetic. Then for any two positive integers a and b, it is nothing but HCF of a and b into LCM of a and b is equal to the product of those two positive integers. So in this case a into b. So then another we need to remember, if p is a prime and p divides a square, then p also divides a, where a is a positive integer. Then we need to know rational numbers and their decimal expansion. If a rational number is given, we can come to know what type of decimal expansion we'll get, whether it is a terminating or non-terminating. Or suppose if decimal expansion is known, what type of rational number it is. Like we know that rational number is expressed in p by q form, so we can accordingly come to know whether what type of q it is. So suppose if x is a rational number, if the decimal expansion terminates, So it is a terminating decimal we are getting. Then x, as you know, in the rational number expressed in the form p by q, and if it is terminating, q will be of the form 2 to power n into 5 to power m, where n and m are non-negative integers and p and q are co-primes. So I hope you understood this. So if x is a rational number, and if decimal expansion terminate, then we can say q will be in the form of 2 to power n into 5 to power m, where 2 and 5, you know that they are primes. Then the same thing, same expression is given in a reverse order. So that is a corollary like statement. Let x equal to p by q be a rational number such that a prime factorization of q is of the form 2 to power n into 5 to power m. So then we have a decimal x as a decimal expansion which terminates. If we are given that x is equal to p by q, where q can be written in the form 2 to power n into 5 to power m, which can be factorized, q can be factorized in this form, then it will be having a decimal expansion which terminates. So it means the same thing but in a reverse order. That is a corollary of this statement. Let x equal to p by q be a rational number such that prime factorization of q is not in the form of 2 to power n into 5 to power m. So in that case, decimal expansion is non-terminating and it is recurring. So it is a non-terminating but recurring. So if q is not in the form, if this denominator cannot be expressed in this form 2 to power n into 5 to power m, then the decimal expansion is non-terminating but it is recurring type. HCF and LCM of three numbers. If three numbers PQR are given to us, the product of HCF of PQR into LCM PQR, if it is not equal to P into Q into R, then LCM of PQR is equal to P into Q into R into HCF of PQR divided by HCF of PQ into HCF of QR into HCF of P and R. Then we can also find HCF of PQR equal to P into Q into R, the product of the three given integers, and it's a LCM of those three integers, LCM of PQR divided by LCM of P and Q into LCM of Q and R into LCM of P and R. So this is how we can find the HCF and LCM of three numbers, but we need to know this condition. So this is all about the chapter real numbers, which you are required to know, such that you will be, once you are familiar with all this, then definitely you will be able to solve the problems of this given in the exercise of this chapter, as well as you will be able to comfortably face the test and board exams. Thank you. Please subscribe.